Good afternoon. How is everyone doing today? All right, let's take a look at our lab 5. So lab 5 is really similar to lab 4, where we have two different objects with different masses. And one of them, because of the weight of this one of the object, the whole system started accelerating in a certain direction. Now the difference is for the Atwood machine is these two masses, instead of one of them is on the cart laying flat, both of these masses are hanging down, and they are the weight is different. So the heavier one is going to be able to fall down, and the whole system is threaded through a pulley. Because this is what called the Atwood machine, and we're going to measure the rate of the falling, the acceleration of the entire system, and as another way to show Newton's second law applications. So our pre-lab today actually is exactly similar to the theory part of this lab, because the theory part is a little bit, we have to do a little bit more complicated. So that's why we do the pre-lab on this particular series. So what I'm showing here today is all in the pre-lab. So let's take a look and go to the pre-lab. Here we have a pulley with two different masses, M1 and M2, hanging on the pulley. And they accelerate together. So we know from the previous lab, if you have a one system, right, you can view the strain and the two different masses as an entire system, so that they will have the same acceleration. M1 and M2 will have the same acceleration, and you can call that A. Okay. So let's, in this case, you can see that the acceleration for M1 is this way. The acceleration for M2 is that way. So the entire system is going this way. Okay. All right. So if we were, now you still have two choices in terms of setting up Newton's laws. One is you can look at the free body diagram for M1 and M2 separately, and you combine these two equations, you can cancel tension. Another way to go about this is sort of a shortcut. I did talk about this shortcut in my lecture course, or if you were from a different lecture course, your instructor may have mentioned it. It's really just by viewing M1 and M2 as the entire system. So if they're an entire system, which force is a force that's responsible for speeding them up? That is a weight on M1, right? And which force is a weight that is a force that's slowing the system down is a weight on M2, okay? Because weight on M1 is dragging them down this way. However, it is responsible for lifting up M2, but the weight of M2 is going downwards, okay? So it's really just a sort of a competition between two different weights. If these two weights are exactly equal, you can see that they're not going to have any acceleration, right? If these two are the same mass and same weight. Okay, so let's go ahead and do the free body diagram on M1 and M2 separately. I'm going to draw the free body diagram on M2. I have, this is the weight of M2. I'm going to label it M2G. And you're going to have tension from the strain. I'm going to label it T. And you can see that that's the two forces. And the same as our previous lab, lab 4, that if you have a strain, we have tension everywhere the same inside the strain. So which means you have the same tension that is pulling on M1 because they're connected by the same strain. So use the same label T, showing that this is the same tension as this one. And there is a force weight on M1, which is M1G, right? Okay, now one more thing is there is also friction. You can see that friction is acting on slowing the entire system down. Okay. All right, so if I were to do free body diagram on 1 and 2 separately, I will have F net equals NA and apply it on M1. I will have force pulling down is M1G and tension pulling up, negative tension, and also friction is in the way of preventing it from accelerating. So minus friction is going to be M1A. If I do the Newton's second law on M2, then I will have tension minus M2G, because in this case, tension is in the same direction as the acceleration A, but gravity is in the opposite direction, so minus, okay? So if I were to label, list the free body diagram and do the Newton's second law separately on these two masses, I get two equations. Then I can do equation 1 plus equation 2. You eliminate tension, right? And you end up with M1G minus M2G minus friction is equal to M1 plus M2 acceleration. Okay, so this is equation that you have seen in your lab manual. You can also get this equation very quickly if you were to view this entire mass as a whole system. So if you view this entire thing as one system, the M1G is responsible for speeding it up. M2G and friction is trying to slow it down in the opposite effect, right? So that's minus. And the whole system is being accelerated. So M1 and M2 combined together have the same acceleration A. So you can see you can get this equation from that holistic view as well. But if you feel like that's too confusing, we can always label the free body diagram separately.
I have a question, Professor.
Yeah, of course.
How come for the second equation, why wasn't friction considered?
Because here that's why, okay, so that's why a holistic view is a little bit more appropriate in this case. We consider friction is an entire overall friction that's throughout the system. But if we want to do the free body diagram sort of on two of them, we kind of artificially have to, you can break down friction and say, oh, some of the friction is on the left-hand side, some of the friction is on the right-hand side, but that's just too confusing. I decided to just say put the friction on the left-hand side. But it's really more appropriate to look at friction as the friction acting on the entire system to prevent it from, make it harder for it to accelerate. So in this case, this is a little bit more appropriate to list that as just one of the influence and making it too harder to accelerate. Does that make sense? This is more of a more artificial way for me to break it down. Okay, because we don't want to double count friction twice. So the friction that was given is sort of an overall friction of the entire system.
Right. Okay. Thank you.
That's a great question. Thank you. Okay, so so having that equation now, what we are trying to do, we're trying to come up way so that we can plot it. In part A of this lab, we maintain the total mass constant. Well, we can do that. So there's 2 cups. Each of the cups have different weights in it. And we make sure that the 2 cups, the total weight, are kept as a constant. Let's say, for example, we keep it as 500 grams constant. However, we are changing mass 1 minus mass 2. So let's say you have 300 more grams on one of them than the other, and then you change it to 250, and then you change to 200. You can keep changing the difference between them, so we get a different acceleration. Okay, so if we were to plot M1 minus M2G versus A, what do we get? So this equation, and let's modify it. So we're trying to plot M1 minus M2G, and you can see that is these two terms that is equal to M1 plus M2A and what plus F, right? So you can see that what we're trying to plot is Y. We want to do like Y is equal to something times, let me say K so that you're not confused by this A. So it's like KX plus B. Okay, so in this case, this is my Y, this is my X, because A is different. We measure A differently using our photo gate. This is our K, and this is our intercept B. So for such an equation, Y is equal to KX plus B, and you're going to plot it, what kind of a graph you will get? Can you describe how should I draw this graph? Predict what it will look like?
Linear.
A linear graph, okay. And a linear graph with a slope of? What would be the slope?
Would it be 10, like acceleration?
In this case, if I were to draw something like this, I would just get my K as the slope, because you can see when X equals 1, Y equals K plus B. S equals 2, Y equals 2K plus B. So if you do rise over 1, you get K. So that is your slope. So if you plot a line that passing through 0, 0, that's going to be Y equals KX. KX plus B simply meaning that the whole graph is moved up by B. So this is Y equals KX plus B, and this is the intercept. Okay, so you should get a line that looks like this. This is our prediction, and this is from our experiment. You will have the data. You will have the data for different Y's, and you have measured data for different A's, and you will fit it to see if it is indeed a straight line and what is the slope and the friction that you measured from your data. We will go back to the data sheet, the data table in a few minutes here. But first, let's do.
Can I ask a question?
Yeah, go ahead.
Okay, so like when you do the when you make the formula, like M1A, equals like T minus M1G or something like that.
Mhm.
How do you decide? 'Cause I was trying to figure this out, and I just made a decision, but I honestly don't know if I was right or not.
Mhm.
How do you decide which one to put the certain way? Because one of them you put as tension minus mass one times gravity, and the other one you put as the other way around.
Yeah, perfect question. This is a great question. So which way I decide which one is positive, which one is negative is basically what you're asking. It doesn't matter which way is positive or negative. You pick one direction and you stick with it.
Okay.
I picked to be whichever my acceleration, since these two are, I'm looking at these two different masses, I don't need to have one fixed direction as my positive. So for example, when I was doing my left-hand side, I chose this one to be positive. So this is more convenient for me because my acceleration is down. I can say my acceleration is positive, and my tension and friction is negative. On the other side, since my acceleration is going up, I'm going to choose my positive to be upward. So my acceleration again is in that direction. So, I'm simply choosing it out of convenience, but you don't have to do it this way. As I said, in the positive direction is whichever you want to define to be positive.
Okay, thank you.
Okay, so now we have that. Let's work on part B. So what do we do? Part B is really nothing new, but with a sort of a little bit modification of our equations here. We want to plot 1 over A instead, and versus M1 plus M2. And here you're holding, and again, you're maintaining the net force, the pure net force constant, but you're changing the m1 plus m2. And again, you get different acceleration. So let me go back to my slide here. What we have derived so far is this slide. So in my slide, I simply took an approach of viewing M1, M2 as an entire system. You can see this picture is in your lab manual, viewing them as an entire system. So might as well draw a straight line showing that, you know, they're all together. And then you get this equation right away. Okay. And again, the way that they define the positive or negative directions is simply pick one and then be consistent with it. So for example, they had picked the right-hand side to be positive, then the acceleration is to the other side, so it's negative. And these two are considered positive because that's in the direction that I picked to be positive, okay? Now you can totally switch that around and then modify this equation, but you'll get the same equation no matter which is positive, which is negative. So they got, okay, so yes, the mass, a more better theory to make it a little bit more accurate is oftentimes we ignore the mass of the pulley. Okay, so, but there is certain mass of the pulley. So a better theory is to try to keep that in mind as well, because while you're accelerating the entire system, you make the pulley, you rotate the pulley as well. So a better system is to consider the pulley's mass in there as well. So we put it in there as a mass of the pulley. Okay, so part A, you're plotting this versus acceleration. Part B, you want to plot 1 over A. So how do we get 1 over A? You simply let's divide by A to the other side so we can get 1 over A. So you can see that if we move F to the other side and divide everything by A, you get M1 plus M2 plus MP on the other side. So from here to here, you move F to the other side, and also you divide it by A, and you get this equation. And we want to plot 1 over A versus what? Versus M1 plus M2. So you need to separate this from the rest of the equation. So this one becomes M1 plus M2 divided by the entire denominator plus MP, mass of the pulley, divided by the entire denominator. So even though this is in such a weird shape, you can see that it is still in the format of y equals kx plus b, okay? And what is your y? Here, your y is 1 over a. And your x, what is your x? Your x is m1 plus m2, okay? So what is your k here? And what is your b here? I want you guys to look at my equation part B and tell me what is k and what is b. Can you see what is k?
Would K be M1 minus M2 times G?
Okay, so let me rewrite this a little bit. So one more page. Okay, so this equation is 1 over A is equal to M1 plus M2 times 1 over M1 minus M2 G minus F, right? So this is really just the first term, plus MP over M1 minus M2 G minus F. Okay, so I'm saying this is my Y, this is my X, what is my K, and what is my B? So you can see this is your K, right? And this is your B. Does that make sense? This is multiply.
Yeah.
Yeah, okay, so
Yeah,
I know this equation, it looks mainly messy, but we can match it up to exactly another linear equation that is y is equal to kx plus b. Okay, so we measure, again, we measure our acceleration using the photo gate, and we vary our x's. We keep the difference between them a constant. So for example, we say m1 become 65 grams. This is 60, so the difference of them is 5 grams. And now we make them 70, 65. The difference is still 5 grams. 75, 70, still difference is 5 grams. But you can see the entire mass M1 plus M2 is increasing. So here, what you're keeping as a variable is the total mass, and you get different acceleration. You can see what we kept constant. We want to keep M1 minus M2 constant because now it is in our slope, and we needed a constant slope, right? We need a constant slope K. Okay, so that is part B. Okay, before we go look at the data table, are there any questions on the theory part? Any questions?
Okay, I have a quick question.
Yeah.
So our y, based off of like the little example you had, our y would be like the 59.
Our Y?
Yes.
Our,
No. I meant our b. My bad. Our b would be the 59.
our B would be this entire thing is our B for part B for the second.
Oh, right. Okay.
This entire thing is B. And yeah, sorry. This is 5 grams, not 59.
Oh, sorry.
Right, these are grams. So which means the difference is kept as 5 grams.
Okay, and that would be our K.
That would give you your theoretical prediction for K, because you can see M1 minus Mg is these grams times G minus little f, and little f should have, you already figured it out from your part A. You already figured out what little f is, right? So you can have a theoretical value what K should be for the second part. And you can predict theoretically what should be for your y-intercept.
Okay.
Okay, so now let's look at the data sheet. These are 2 different cups, and each of the cups have some weight added to it. And the added mass is listed here, but you have to go ahead and read the mass of each of the empty cup from the video and add that together. You get the total mass 1 and total mass 2, okay? And then list all the differences in the masses, because the differences is the difference between M1 and M2 is different for each of the trials, and that difference gives you the net force, and then you measure the acceleration directly. The video will tell you what the acceleration is. Okay, so let's take a look at that part of the lab. 1 second. Okay, let me switch it to the video.
Folks, we should be able to get to have the cup.
Okay.
The masses in the will start with 56.
You can see that this is a measurement for cup 2. You can see the scale is blown up a little bit here, somewhere around 5.9 grams. That is how much, what is the mass for cup 2. So you need to read the cup 1 and cup 2's empty cups and add it to the added masses together. Okay, and then when they, later on, they start taking the data sheet, and it's really, I think this is really interesting to mention. They have a place where they show you the, want to see if I can show you.
Start with 56 grams. The masses in this video, M1 and M2, are only the added masses. Don't forget to add the cup into that. For part A, holding total mass constant, let's get our computer set up. Open our reference or should be able to verify calibration. Begin. Here's your acceleration, but we do need to check
Oh,
it.
okay,
So
so
let's open.
the right-hand side, you can see on the right-hand side of the screen, this pulley has a few different spokes poking out, and what the sensor is reading every time something passes by, one of these, a little radius pass by, it blocks the sensor and able to let the sensor know how fast it is spinning. So what the program does is, as the whole entire system accelerating, the pulley is spinning faster and faster. So the sensor is translating that rotational motion to a linear acceleration for us. But we should know where that data comes from. Okay, it's coming from the pulley's rotation. Okay, so that's why
Open
it's
up
able to
our
measure.
graph data, browse application of.
So you can see that the software reads an acceleration, but then you can also double check the acceleration using the graph. So here it shows 26.65. That is the acceleration. If you go back a little bit to where the data was showing you the acceleration is 26.65. And that is your acceleration for the first data trial. And they will do this, repeat this for all the differences, different masses they use, and that is what you're going to measure for acceleration in part A. Okay, so let's go back to our data sheet, data table. Oh, okay, so it's over here. Okay, so you got your x values as your acceleration. You got differences in masses times 980. Again, we use 980 for g. You get your y values. You plot the y versus x. This is your y. This is your x. And from the data, if you plot using Excel, you say add trend lines, show an equation. They will show you an equation. So if, for example, they show you y equals 5x plus 8, then you know the slope is 5 and the intercept is 8. That is what you can read from your data, right? And you know that 5 is going to be your slope, and your f is going to be intercept. Okay, so that's an example of what the data might look like, something like this. And we got a question that whether would I be posting this recording? Yes, I will post this recording afterwards. Okay, so that is just our part A, right? And you can see from the part A, let's say your slope is, I don't really know, 1500, for example. And that means that total mass of M1 plus M2 plus the mass of the pulley is 1500. So from that, if you subtract mass 1, you know what that is. If you subtract mass 1 and mass 2, you can get effective mass of the pulley also from the slab. It's an indirect measurement, okay? Now part B, we have went through. We are keeping the differences constant. You can see they all have a 5 gram of difference, but each of the masses are different. So that you are again plotting the x and versus y. So be very careful. For part B, our x and y are switched. Our 1/a acceleration is now a y. You're plotting it in the y direction, y axis, and your total mass is now your x values. Okay, so be careful, don't reverse them, because if you reverse x and y, your slope will be reversed, will be 1/, the value you actually really need to get. Okay, so in this case, you can see what is my slope. This is a slope you read from your data. This is your slope you read from your data, but you know that corresponding to your theoretical value, your slope should equal to 1 over m1 minus m2 g minus f, and your y-intercept should be mp over m1 minus m2 g minus f. Okay. Is the slope larger than 1 over m1 minus m2 g? Well, you can see that our actual slope is 1 over this minus f. So minus f make the entire denominator smaller. So 1 over a smaller value give us an overall number that it is going to be, yes, larger than just 1 over m1 minus m2g. Okay, so that's, if you had not considered friction in this lab, then you will get this slope, and that's not going to be very accurate. And then consider friction, you should find that your data would be better improved because it's a better model. You have considered the actual friction that could be present in the pulley, right?
Here's your acceleration, but we do
video.
need to check this. So
Go back to the video. Let me see if I can find the next section. Part B. They keep the difference with 5 grams always, and everything else stays the same. Okay, and then they start recording data, and you can read your acceleration here 228, or you can read the acceleration already in this. The acceleration is 228. So either way, the video will tell you the acceleration. Okay, so that's all for this lab. Are there any questions so far?
I have, I guess, a bit of a question. In my lecture class, we actually haven't considered the mass of the pulley when working on these types of questions. Will the mass of the pulley be given to us?
In the lecture course, indeed, we do not consider mass of the pulley because when we're doing theories, when we do lectures, we say, consider you have a light pulley, your pulley's mass can be ignored. But for this lab, considering the mass of the pulley will overall improve the results because indeed will affect the result. The mass of the pulley here, we do not directly measure it. You can see we never measured the mass of the pulley, but you can get the mass of the pulley indirectly. Where did you get it? You measure that from your part A, you get your slope, and you subtract the total mass M1, M2 from your slope, and that is your mass of the pulley.
Right, okay.
Yeah, so you can actually you can measure mass of the pulley from your data, even though you do not take the pulley down and put it on the scale. We can still get the mass of the pulley.
Okay. All right. Thank you.
Any other questions?
So I had a question. So we don't have to calculate for friction once we do the Excel graph. Our y-intercept will be our friction.
For your part A, you mean?
Yes,
Yeah,
and part
F
B
is your the y-intercept is indeed your friction. Yes. So part A, the intercept directly read from the graph is your friction. For part B, you also measure a y-intercept, and that is this entire thing. And you can see that if they match. So for part B, you can plug in the mass of the pulley as you measured from the previous part A, divided by M1 minus M2, which was kept at 5 grams for this part, 5 grams times G is 980 minus friction, again, the friction from your previous part. And that is your theoretical value for the y-intercept for part B. Does that make sense?
Yes, it does. Thank you.
So yeah, you read one intercept, you read a number from your graph, and you compare with what the formula gives you. Any other?
Thank you.
Thank you for the questions. Any other questions? All right, so if not, I will upload the slides as well as our video recording afterwards, later today. I'm not sure if I will able to do it right now, but as soon as I can, I'll upload it. Okay, all right, so that's all for today. I will see you guys next week. Bye, everyone. Have a good rest of the week.
Thank you, Professor. Have a good day.
Have a good day. Bye-bye.